And you should also be able to see my screen.
Yes, we can.
Okay, then let's start. And thank you for us turning up here, because indeed this is about mixing hardware and software, and I think it's quite a cool topic to think about when you are a .NET developer, because .NET nowadays becomes more and more low level, or shall I say, more and more low level features are available to .NET developers. .NET itself is not becoming low level. So think of, for example, vectorization, so vector-based computations, single instructions, multiple data, everything with span T and memory T to avoid memory copies, all kinds of tricks to avoid allocations. And now, what I would like to show you is how you can go even more low level and take your .NET software and turn it into an actual piece of logic hardware. But before going into that, a little bit of introduction. I'm from a company called Lombic Technologies. We are mainly focusing on .NET, ASP.NET Core-based web development with the CMS Orchard or Orchard Core. So if you are working with the web in .NET, I very much recommend you check out Orchard Core. And we are mainly working with companies from Western Europe and North America, including the Fortune 500 company Live Nation, Microsoft itself, or the Smithsonian Institution. But when we are not doing web development, then we are doing some research and development, like our Hastlayer project that I will show you. But before that, let's actually talk about you. Now, let's suppose that you are doing some number crunching, so some performance-heavy computations. And to be more specific, I mean something in the areas of, for example, artificial intelligence, machine learning, including the now quite popular large language models, or something with images, image video processing, computer vision. At the core, these have a lot of similarities. Or you are doing algorithmic trading on a stock market, or high frequency trading even. Or you are working with huge chunks of data and you need to compress them. Or something that has to do with cryptography or cryptocurrencies even. Now, let's suppose that you have an algorithm in these areas and you want to make it faster. So what can you do as a .NET developer? Now, the first step would be always to figure out what's slow. So you would profile the application or the algorithm, check where it spends the most amount of time, and then you will try to optimize it. Let's suppose that you have already done that. Then you may want to parallelize your algorithm. So run it on multiple threads, with the task parallel library, for example. And let's suppose that you have already done that as well. And finally, of course, you can always use, well, to any limits, you can always use faster and more hardware, so you can scale up or scale horizontally out, which in the cloud is especially easy. But let's suppose that you have already done this as well, or you can't just throw more money at the problem. So if you have infinite amount of money, you can still pursue these avenues, but you have run out of feasible options. Then what you can look at or look into is heterogeneous computing, namely doing something with usually GPUs, video cards, or perhaps FPGAs. And now let's talk about last part a little bit more. FPGAs or field programmable gate arrays are basically computer chips that can behave like any other computer chip, within some limitations, of course, since they all have a specific capacity. This means that they can be dynamically rewired pretty much. So, for example, if you want an FPGA or if you want a chip that computes some physics calculations, you can program an FPGA to do that. If you want algorithmic trading on the stock market, you can program an FPGA to do that. Now, if you haven't used FPGAs directly before, I'm pretty sure that in some way you have already used them. For example, if you Google something on Bing, uh, then you have used them because Bing is accelerated by FPGAs. Or if you have used Azure, then as well because Azure uses FPGAs for networking. But FPGAs are also sometimes used in household appliances like routers or X-ray machines, which are less household appliances, or self-driving vehicles even. To utilize them, you have to be a hardware engineer since it's basically hardware engineering. You build a piece of logic hardware. Now, to alleviate some confusion, FPGAs have nothing to do with something like a Raspberry Pi, although they also have visible circuit boards, because Raspberries are just small computers. And similarly, Arduinos are something completely different, and Arduino is a microcontroller platform. Now, why would you use FPGAs to begin with? And there are computing benefits to it. So when we are talking about accelerating computations, FPGAs have some unique computing benefits. So let's compare them in a totally non-scientific, very approximate way to CPUs and GPUs. And let's talk about parallelism first. So how many things you can compute at the same time? And CPUs are on the lower end here, I would say, because a CPU can have, like 8, 16, 32, 64 cores, but that's about it. GPUs on the other hand, are highly parallelized devices. They have thousands of little processing cores. Those are very different from CPU cores and very simple compared to CPU cores, but still. And FPGAs are kind of in between here because although an FPGA doesn't really have cores, although that's not true for every FPGA, the degree of parallelism you can achieve with an FPGA is in the order of magnitude of hundreds. Now, let's talk about the complexity of programs with FPGAs. With the complexity of programs you can run on these devices. And CPUs win here, I think, because if it's a program, you can run it on a CPU. And GPUs are again on the other end, but on the lower end here because GPUs have much simpler programming models. Whereas with FPGAs, although you are not really programming an FPGA, the complexity of algorithms you can execute with an FPGA are somewhere in between. So to take a look at the two charts until now, you can see that FPGAs can already have a computing benefit here because they are pushing the complexity of CPUs or they're pushing the availability of the complexity of programs you can run on them of CPUs, but they are also pushing the parallelism of GPUs. And lastly, one thing where FPGAs really shine is power efficiency. Because CPUs and GPUs are roughly on the same level here, I would say, but an FPGA is really power efficient. And this is because you basically hardwire what you need it to do. There are no operating systems to run, there's no operating system to run, there are no other software to run, there's no memory management, nothing. It just does what you need it to do. And this power efficiency translates to operating costs, of course. So when we are talking about the data center, it might not matter that much how many watts you consume just for the sake of watts, but power consumption is cost, and power consumption is actually cost twice because you also have to dissipate away that heat. You have to cool the data center. But there's a downside with FPGAs, is because programming a CPU is easy enough. Programming GPUs can be as well, but utilizing an FPGA is really, really hard. And the reason for it is that you are doing hardware development. It's super low level. You have to think in terms of logic gates and wires and clock cycles. It's not like programming at all. But with high-level tools like Hastlayer, we intend to bring this down onto the software development level. Speaking of which, what's actually Hastlayer? This magical thing that allows us to develop for FPGAs. And Hastlayer is basically a tool that takes a computer program and turns it into an equivalent FPGA logic. Or we could also say that it takes a computer program and creates an equivalent computer chip, hence our tagline. Or we could also say that we take the logic which was previously expressed as software form, and we somehow try to create an equivalent logic that computes the same thing as hardware form. And of course, we are not just talking about any software, but .NET. And it's actually .NET, not just C#, because Hastlayer processes the .NET assemblies. It decompiles the .NET assemblies, and because of that, not just C# can be used, but any .NET compatible language. So to summarize, what we aim for with Hastlayer is to get all the computing benefits of FPGAs for us software developers. So that means that you can get a performance increase for algorithms that are highly parallelized and compute bound and or memory bound. At the same time, you can get a higher power efficiency, so lower operating costs. And thirdly, it's just programming as usual, so not much new things to learn. Now, a lot of talk until now. Let me show you some code. So I'm switching over to Visual Studio. And what we see here is one of our examples of Hastlayer. This and every code and everything else that I show you here today is up on GitHub, by the way. The whole of Hastlayer is open source. You can check out everything in detail. And we also have a lot more examples there. But this example is called a parallel algorithm. And well, it might be telling from the name that this is a highly parallelized algorithm. This is actually not a real-life algorithm. This is kind of an exaggerated example of the kinds of algorithms that are especially suited to be accelerated by Hastlayer with FPGAs. And what it does is mainly here. So it has some conditional logic, which is executed 10 million times. Again, this is not a real-life example. This rather demonstrates or mimics some kind of number crunching. And this logic here is executed in tasks. Is everybody familiar with tasks here? Shout if you aren't. Oh yeah, great.
Yeah.
Okay, it seems everybody is. Fantastic. Now, we are starting tasks here, this many in a loop, and this many is actually 260 here. Now, why 260? Because this many will fit on the FPGA that I have here, what I will also show you in a minute. Because when Hastlayer processes this, then it will basically create a 260 core processor just for this class. And this many cores will fit on an FPGA. When we run this on a CPU, then due to us using tasks and not low-level threads, then 260 tasks will be started, but that doesn't translate to actually 260 threads. Only that many threads will be started. How many are efficient to execute on the current CPU? Otherwise, in these codes, there's some further plumbing here. Wait for all of the tasks to finish, and then we produce an output from all of these tasks. What will be the output of the whole algorithm? So let me actually run this. And I mentioned that I have an FPGA here, and this is it. Showing it to the camera now. This FPGA here is the same that goes on board of a satellite. I wanted to make it a little bit more interesting for you. And we all know Azure and the cloud. Hastlayer is available there as well. But I'm sure that you didn't know that you as a .NET developer can also program satellites. So this is what I'm remoting to in this shell. This runs a little Linux. And what I'm running here now is a demo application. What I've shown you, this onboard computer that goes on board of satellites has an ARM CPU, so something that you also have in your smartphone. It's a 2-core ARM CPU that's packaged together with an FPGA. It's called the Zinc platform, and it's widely used in space tech applications and also onboard of drones. And it first executes this parallelogram sample on the CPU part of the Zinc, and then secondly, it executes it on the hardware part 3 times. So let's see what the results are. And the results are here. On the CPU, it was roughly 25 seconds. So this took quite a lot of time, frankly. Let's see the hardware execution. Let's see how much it took on the FPGA. And if we scroll down a little bit, we will find the results here. And the result is that it took around 240 milliseconds when we only talk about what's happening on the FPGA, and roughly 330 milliseconds when we also take the communication round trip with the CPU into account. But this was the first execution, and at this time, there was also time spent on JIT compilation for .NET, and the caches weren't warm. So when we do this repeatedly, then like on this second time, it took around 250 milliseconds. So this was about 100 times faster than on the CPU. Now, again, this is not a real life example, but you get the idea that you can get 100 times speed improvement just by utilizing Hastlayer, which is quite a lot. And going back to Visual Studio, just one more thing I wanted to show you is that previously I've shown you the parallel algorithm sample, and this was just a single class. Now, of course, you also have to somehow call this run method on this class. So how does that happen? How are you actually running something on the FPGA? And how that happens is demonstrated here. This is a little console application. And again, it's part of the SDK, which is up on GitHub, so you can also check it out in detail. And it demonstrates how you can call into what Hastlayer makes it available, how you can use Hastlayer from the rest of your application. And well, first, you need to do some configuration, which is basically selecting which FPGA you are using, and then secondly, telling Hastlayer where the whole algorithm of yours starts. Then you need to instruct Hastlayer to generate the hardware, which happens on this particular method call. This is what generates the hardware implementation. After that comes the execution itself, and how you run something with FPGAs on Hastlayer is like this. So these 3 method calls here are the 3 method calls that I've shown you. And that's it. There's not much special. You just call methods. Actually, there's one thing that's special here, this particular line, where you take the instance of your class and wrap it into a dynamic proxy. This allows Hastlayer to hijack method calls. So this allows it to hijack this run method call, and instead of letting it execute normally on the CPU, it will transfer the execution onto the FPGA. This, by the way, also allows you to dynamically execute something on the FPGA. For example, if some computation is trivial based on the input parameters, you can just compute it on the CPU, because then the overhead of calling into an FPGA wouldn't make sense. Now, you may be wondering, okay, this is how I use Hastlayer, but how does it actually work? How is the sausage made? And this is the FPGA that I've shown you here. This is the little onboard computer that goes on board of a satellite. The FPGA chip itself is that little thing in the middle. And as mentioned, this is not just an FPGA, but an ARM CPU and an FPGA together. The whole thing actually plugs into this motherboard. This is something that I've also shown you. This has some peripherals, a USB port, Ethernet port, you name it. And a little bit of peek into the hardware implementation, just so you can see something that perhaps you haven't seen before. And what I'm showing you here is some code. It's some code written in the VHDL language. And that's actually a hardware development language. And what you are seeing here is some hardware code. Although you can see familiar things like function, begin, there's also an if-else here. This is not a program. This is not software code. Rather, this is all hardware code. And some things might be familiar to you and some things might be similar to software, but actually it's very different when we go into the details. And why I wanted to show you this is because if you scroll down a little bit, then we'll see something familiar, parallel algorithm here. And this block here actually, it corresponds indeed to our parallel algorithm class. It's actually a couple of type declarations, so this is not the whole implementation, not the whole hardware implementation of that class, just some types. But why I wanted to show you this is because check this out. It has the index 0. And if you scroll down a little bit, it's the same thing, but the index 1. And then index 2. Now, you may guess where this is going. If you scroll down a little bit more here, we'll see the same thing again with the index 259. Now, remember that in parallel algorithm, we had 260 as set as the degree of parallelism. This is how many tasks we started here. This is where the 260 comes from. And in the hardware code, this is where we see the 260 copies of our algorithm. This is where the 260 core processor, so to say, is created. And this is where all of the performance and power consumption benefits of FPGA computations come from, because you can create your own kind of processor for your class, for your algorithm, which makes it very, very efficient because you can get specialized hardware. Now, a couple of other things to show you. What else we are working on? Hastlayer actually supports the VITIS platform of the FPGA manufacturer Xilinx, which means that with some relatively small amount of work, we can support a lot of FPGAs. This includes high-performance cards. They call them data center accelerator cards that are available in data centers. This includes also all major cloud providers. So AWS, Azure, Baidu Cloud, these all have FPGAs that Hastlayer supports. And this also allows us to support aerospace applications, like I mentioned. We also created some benchmarks, the details of which are also available on GitHub. And here are some numbers. We have done some benchmarks with some sample code in the cloud, so with the high performance data center accelerator cards. And we have seen something like something from 4 times speed increase up all the way to 30 times, and similarly from 20 times the power consumption decrease up to more than 100. Here we benchmarked these high-performance data center accelerator cards against high-performance CPUs in the same machine. We similarly benchmarked this Zinc based platform, this onboard computer design that I've also shown you, And here we have even seen nicer numbers. But again, these numbers are comparing the CPU and the FPGA on that device within that platform. So while the Xinx FPGA was a lot faster than the Xinx CPU, the high-performance data center accelerator cards were a lot faster than that, of course. We have also created our own number implementation for .NET because you may know that .NET uses double and float as floating point number formats. And those were great, but there are actually better number formats nowadays, better in terms of having better range and better accuracy. And one of those is called posits. This was invented by a mathematician called Dr. John Gustafson, who is working on this in Singapore. We have created a posit struct in .NET and a corresponding .NET library. And it's Hastlayer compatible, so we could already turn it into a hardware implementation. So it's a pretty cool thing, I think, that you can create your own number type and turn it into its own processor with a push of a button. Now, we want to have more use cases. So if you have some high performance computation use cases for .NET, please let me know. I would be very curious to see where Hastlayer can be potentially used. We also partnered with the Wigner Research Center for Physics to test out Hastlayer with physics computations. And be aware that FPGAs are available in every major cloud provider and are coming in other data centers as well. As mentioned, AWS and Azure already have FPGAs also. And Intel, which is the largest CPU manufacturer, recently acquired the second largest FPGA manufacturer called Altera. And AMD did the same thing with the biggest FPGA manufacturer called Xilinx. So the CPU manufacturers also know that you can't just increase the performance of CPUs indefinitely. You need to have something new, some new approach. And FPGAs can provide that. So to wrap up, if you like this, and I really hope you did, then please check out the SDK. Everything that I've shown you today and everything else of Hastlayer is up there on GitHub. And be ready, because I think FPGAs are coming. So thank you very much. And if there are any questions that you would like to discuss, I'm more than happy to do that.
Thank you very much.
Thank you.
Thank you very much.
Thank you for your attention. It seems Stefan has a question.
Yes. How does this work on a? I can't really draw the connection between the C# code I write and then the hardware instructions being produced and run. Where is is this part? Is there some MS build? So how does it work on a compiler and or runtime level?
Great question. So let me show you this. So I've shown you the code here on the left-hand side, how you would integrate Hastlayer into an existing application, or how you would call into the code. And on the right-hand side, I've shown you the hardware code that Hastlayer generates. So I haven't shown you the whole story. So here it is. What basically happens is that on this method call, Hastlayer generates this code on the right. This is yet the code. So this is not yet. This was a transformation step from .NET to the hardware code, but we don't have the hardware implementation ready yet. On this method call, what also happens is that Hastlayer runs the tool chain of the FPGA manufacturer, in this current case of Xilinx, to what we call generate the bit stream. So that will take this code and do kind of a compilation step there. Hastlayer then will also what we call program the FPGA, so load that bit stream, that compiled hardware implementation onto the FPGA, onto the actual chip. And at this point, the FPGA will be ready for work. So when these method calls happen here, then Hastlayer will be able to communicate with the FPGA. On the FPGA, we also have kind of a framework that handles that communication. So it's not just something just working, but we also have the communication ready from the .NET side and also on the FPGA side. So at this point, from .NET, we send input data to the FPGA, we receive output. In both cases, there is a serialization and deserialization happening, and in the end, receive the .NET outputs.
So in that case, what do you use the memory configuration for? Or what do you need? Because you mentioned there is no memory. So does the FPGA has its own memory, or does it then use the RAM from the computer? How does memory management work?
I didn't mention this because this is some more advanced stuff here, but this memory configuration is about configuring Hastlayer's memory. And that's actually what's on the FPGA. Because yes, the FPGA has its own memory. What this means is that when and this is something that you don't have to think about when you are using Hastlayer. I'm just telling you because, well, this is what you asked, and it's interesting. So what happens is that when we send inputs to the FPGA, which happens on this method call again, then on the FPGA side, those inputs will be written into the memory of the FPGA. Usually that's actually some kind of RAM, but it's a separate RAM on the FPGA card. And usually it's some kind of high bandwidth memory as well, which is, well, fast. Then on the FPGA side, we can interact with that memory. That's something I haven't talked about, but when we go back to our parallelogram class, you can actually do that interaction here as well. Here, you see that our run method, by the way, this is just a name we have chosen. It doesn't have to be called run. This run method has a simple memory method argument, which is kind of an API to that memory. So this is where we can read and write into that memory. So basically, you see we have read methods, and there are write methods, which serves as some kind of local memory for inputs and outputs, and for dynamically allocated memory as well. But this is also something that you don't have to think about too much usually when apart from input and output handling. Because as you can see, if you just create a variable or something like that, then you don't have to manually allocate memory or something like that. This is for things that don't have a static size. Like when you are generating noise, for example, that's parallel noise generation is actually also one of the use cases of FPGAs, and that noise is either unlimited or doesn't have a static size. Then you can use this memory to use it, well, as much as is available, but the size being determined only in runtime.
I see. So do I need to worry about the memory available on the FPGA, or like, do I really not need to care about this at all?
If you don't need to use more than what's available, then you don't really need to care about it. But actually, Hastlayer is throwing an exception if you try to do something that wouldn't fit into that memory.
I see.
Something that you have to, something that's coming from this memory configuration actually, is telling Hastlayer how much memory at maximum you want to use. And if you run out of the physical memory, or if you try to do something outside of that memory, outside of that available memory, then you will basically get exceptions.
So I could like artificially limit it in like a test case scenario to simulate FPGAs with lower available memory, if this is a thing. Do I get it right?
You could do that, yes.
Okay.
I'm not sure why you would do that, but that's definitely possible.
Just theoretically. I think more of a question if I understand the concept correctly.
Oh yeah, yeah, sure.
Yeah, I hope last question. So okay, so you're not compiling C# into the I forgot the name, VHDL, but the assembly code, right? The IL code.
Yeah, please continue, because this is not yet the IL code. Yes.
So do I get it right? You're then taking the IL code and then converting this into the VHD.
Yes, pretty much, yes.
How does the call? I may misunderstand this, but how does the system, how does the hardware level now call back into .NET method? So let's say I use some .NET 8 method. Is all of the .NET methods supported? Is there potentially some limitation of available BCL methods, or I guess there is something that I don't understand yet.
Yeah. So the example that I've shown you here is very simple. The reason I've shown you this is because specifically it's simple. So one of the things it doesn't demonstrate is calling pretty much anything apart from something on the simple memory, the taskbar library, and that's it. It doesn't show calling other methods, either from this class or from other classes, and it doesn't show calling anything from the .NET API, from the .NET base library. Both of them are actually possible. And how it works, I think actually both of them are demonstrated. What I'm showing you here is the SDK again, and we also have some more samples here. I think in this one, let me quickly check. Not this one. Well, I'm not really sure, but then let me explain otherwise. What happens is that when you call this mentioned generate hardware async, you have to pass Hastlayer all the assemblies that you want to process. In this case, since this parallelogram doesn't use anything, we just pass that one. And what Hastlayer will also do is that it will process only and convert into a hardware implementation only what you tell it that you want to call from the outside. In this case, we told Hastlayer that the entry point is this parallelogram. Now, if this parallelogram would call other methods on itself or other methods on other classes from the same assembly, then Hastlayer would kind of explore what is actually being used and also process those parts. And you can also actually pass in the assembly of a .NET method. Now, if it's something that Hastlayer can process, and Hastlayer has limitations, which is documented, so not everything can be processed here. Not everything is compatible. There are limitations. But we have checked out something like some of the math, some of the methods on the math class. Not all of those are actually compatible, but not because not all of those are actually implemented in .NET, but they call out to some other native API. But then you would also do something like this. And then if you call methods on that math class, then those specific methods will be also processed by Hastlayer. Just those, so not the whole of .NET, but just those methods will also be turned into pretty much VHDL.
I see. Okay, so I'm basically telling it what to compile down to via Hastlayer to the hardware level in order to get it all running. Do I get it right?
Yeah, pretty much,
Okay.
yes.
I see. And yeah, I may come back with another question in a minute or so.
Sure, great question. So thank you. And unless anybody else has a question, there's something in the chat. Oh, Javier said. Javier also has a question. Is the FGPU meant to always be connected to a computer, or is there a way to send the algorithm to the FGPU and then disconnect? Am I confusing an FGPU with an Arduino? What I think Javier means by FGPU is FPGA. And FGPU is probably a thing as well. But is it possible to use the FGPA without a host PC? And the answer is yes. We don't support that specifically with Hastlayer. I mean, we don't have it cushioned, but it is actually possible. The model that we are shooting for with Hastlayer is the hardware acceleration one. So you have a .NET software. Some part of it is slow. That part is an algorithmic part, so it's not slow because of network I/O, for example, but because it computes something that's hard to compute. Then you offload that onto an FPGA, use that FPGA as kind of hardware accelerator, kind of an external processor, but the software is still mainly running on a host PC, meaning a server as well, of course. I'm just talking about the architecture when mentioning PC. But of course, it can also be an ARM-based computer, as we have seen. Now, it's also possible to actually have FPGAs without a host PC. Something that, by the way, happening a lot in the mentioned algorithmic trading example too. So there, when we are talking about high-frequency trading, then FPGAs are sitting on an Ethernet network and are directly communicating with the servers of a stock market. There's no PC, nothing else, just an FPGA on a network. Now with Hastlayer, how this is possible is that, let me go back to the VHDL. So you will be hardware developers by the end of it. What we see here is not here. I'm trying to show you this one. Yes. What you see here is that what Hastlayer generates is kind of a hardware component. It's something like a function, or rather, this is more like something a class. But again, it's a very different concept. And this has some input and output, and the inputs and outputs you can see here. The input is, for example, a bus called data in, which is a 32-bit bus. Data out, the outputs is also a 32-bit bus, and there are a couple of other what we call signals here. Basically, all of these are a bunch of wires going into our hardware implementation. Why I'm showing you this is because this is actually very simple. Well, it might not seem to you at first glance, but in hardware design terms, this is a very simple interface. And that means that you can take this hardware implementation that Hastlayer generates, this component, and you can plug it into another hardware implementation. So it is also possible to create a hardware implementation either manually or buy one, or have an existing one for whatever reason, and then extend it with Hastlayer, then add the core of your logic with Hastlayer, and using this interface to communicate with that component. So in that way, you could create a different framework of such, and use whatever Hastlayer generates on its own without a host PC. And I hope Javier will let us know from the recording whether this actually answered the question. By the way, anything else? Oh yeah, Ivan left. So yeah, anything Glass you would like to know, Stefan or Stefan? Stefan, by the way.
Stefan, thank you. If you don't mind,
Sure.
What happens if I call into hardware intrinsics? Will this just throw an exception, like this is not available?
Any specific one you mentioned?
No, not really. Well, I haven't used the hardware intrinsics all too much, but what happens with algorithms if they call into well, I guess the vector of t, can imagine that works, but what about using hardware intrinsic? I haven't really used hardware intrinsics, to be fair, but would this work, or would this throw not available, not platform not supported or something?
It's definitely not supported, unfortunately. I'm not actually sure what you would see. You would see some kind of exception, for sure. So when Hastlayer encounters something that it doesn't understand, then of course you will get some kind of exception. So what kind of limitations are in there is, as I mentioned, documented. It's also documented what's specifically supported. So perhaps that's actually the better way to start, because Hastlayer has its limitations. Not everything makes sense on an FPGA. Actually, hardware intrinsics, from the top of my head, I don't believe any of that would make sense. Or something like writing to the console doesn't make sense on an FPGA. And some things are just not supported because, well, we didn't have time for it. Nobody asked for it yet. So all the important stuff is supported, I think. If you encounter something that you really need and have a good use case for it, then please let us know on GitHub, and we'll look into implementing it.
I see. So okay, I think now that the dots connect, how this is working.
I'm glad to hear.
Yeah, cool. Thank you very much.
Well, thank you very much for the questions. All great questions. And again, please let me know. Here's again my contacts. If you want to do something with Hastlayer, I will be happy to help. Otherwise, there's GitHub, so all the usual interactions, ways of interacting are available on GitHub.
What would be the cheapest way to start, just to give it a try? Running is a cloud solution the least buy-in thing? I
think yes. So the cheapest cloud option, at least in Azure, is something like $1 per hour. That's only for the FPGA virtual machine, so you don't need that for all the time. That's just when you actually want to run something on the FPGA. That's perhaps that would be the cheapest. This specific thing that I've shown you here is something like $300 US, 250 euros. It's, by the way, by the company Transelectric that you may know. Are you from Germany or Austria?
Yeah, yes, Austria.
Austria. Yeah, well, it's a German company. So then only the language is the common thing. But anyway, of course, Trans is quite well known for a lot of stuff. So figured perhaps you have heard of them.
Not yet.
Well, then now. Of course, the question is what would you like to do? If just to play around, then any of these options would be sufficient.
But it can't really be emulated, can it?
It can actually, but that's more like a hardware engineering thing. If you are interested, of course, you can do it, but we don't have specific support for it. That's the approach would be their approach there would be the same that hardware engineers do, starting with something that's called a waveform simulation, which basically means that a simulator takes the VHDL, it behaves like hardware, but all the outputs you get are pretty much bits.
So final question.
Sure.
Since you said okay, some stuff is not supported, such as console white line, is there like, do I get a warning during compilation or an error saying that this is not supported, this will not work at runtime?
Yes.
Okay, cool.
Yes. Actually, we can also try. Let me go back here. So console write line is something that's not supported. So we can check out what actually happens. I think what will, yeah, well, we actually get a code analysis warning here as well, but that's something else. I think the first exception here we'll get is actually that this method can't be found. It can't be found because we didn't add the assembly of console.writeLine to begin with. Yeah, so that's the exception. Oops. That's the exception that we already get. Oh, sorry, I wanted to show you. Yeah. So did you forget to add the assembly? Yes, we didn't actually add it. Now, I happen to know that if you add the whole of .NET to the compilation, then it will, to the hardware generation specifically, then it will take some time, but we can check out. It will take a couple of dozen seconds, I think. I'm not sure which assembly console is in actually, but we can try.
Isn't it all like the core lib actually? So isn't this like quite huge?
I think it will be it, yes. And we already got a not supported exception. Oh yeah, this is one of the exceptions. And such an exception is actually something that that's more similar to what you will get when you try to do something in the code that Hastlayer can't do. And yeah, so base is not supported.
Cool. So I'm just wondering about so like pitfalls are unveiled early.
Yeah. I think the best option is to start by writing some code from scratch just to process with Hastlayer. So while the intended goal of Hastlayer is that you take your algorithm and it just works, we are not there yet. So kind of working back from an existing algorithm to make it Hastlayer compatible is hard. Otherwise, if you just try to run some code or write some code, process it with Hastlayer, see if there's an exception. If not, then continue. That's easier. By the way, it's mentioned on GitHub, but I didn't mention that how Hastlayer processes the IL assemblies is with the decompiler of ILSpy, which was mainly written by Austrians, by the way.
Yeah. Cool. The world isn't that big after all. Cool.
Yeah, and they were also super helpful when we opened some bug reports, asked for some help.
Cool. Next time I meet one of the maintainers of ILSpy, I'll ask them about how painful Hastlayer was. No, how enjoyable, of course.
We didn't have that many issues.
Cool. Okay, I said it 2 times already, and I think 3rd time's the charm. One last question, then I'm done.
Right,
about
sure.
the POSIX float numbers.
It's in this
Is it
code
like,
posit. Yeah.
Should I so to get the most out of it? Should I actually? So is there a .NET representation of this type, and to get the most out of the algorithms on the hardware, should I then use that type over the built-in .NET numeric types? Or will it be automatically doing the conversion and stuff?
Unfortunately, not yet. We won't have an automatic conversion. Although actually, supposedly posits are drop-in replacements for floats, and can also for doubles depending on the size. But we are not doing an automatic conversion of that yet. And by the way, the implementation of posit is here. So yeah, posit 32 is a 32-bit posit. We also have other sizes. This is
Mhm.
also up on GitHub, also open source. Now, you asked whether to make most of the system, you should use this. Well, actually, if you need floating point computations, then you need to use this. Unfortunately, we don't support the built-in doubles and floats. Double and float is something that's not actually implemented in .NET. That's a low-level thing, so you can't compute that. If you don't need floating point specifically, you just need to do calculations with fractions. Then you can also use fixed point, for which we have an implementation, which is actually there. Let me search for it. It's it's not Lombik.algorithms, but Hast.algorithms. It's in a different library / package. We have 64-bit fixed point number type, which is fully compatible with Hastlayer as well. So for fractions, but not for floating points. This is a better solution because it's simpler, and because of that, faster.
I see. Now I want to ask another question. I'm such a fool about generic math support, like the language. This seems tough because that's also on the .NET runtime, isn't it? That sounds. Can this be theoretically supported?
Sorry, I don't know what you mean. Math? What was
the generic math feature that you can have. That you can have static abstract members on interfaces, like, for example, Fix64 could implement the I number interface, but I guess this is two different worlds, isn't it?
We never looked into that. So I don't know. I don't know how hard it would be to support that. I don't think we support it yet. Well, we surely didn't test. I'm just not saying that we don't support it yet, definitely, because there are sometimes surprises. And the reason for that actually is that that a lot of the cool things in C# are not implemented in .NET, not implemented in the .NET runtime or by the .NET JIT compiler, but by the C# compiler. Static members on interfaces specifically, I don't know, but for example, properties are, I think, properties I think are a C# thing, not a .NET thing, and because of that, the cool thing is that we are decompiling .NET, so that means that we are working with a simpler version of your code, pretty much. And because of that, sometimes there are things that we don't specifically support, but still, since it's compiled and it's turned into a simpler thing when it comes to the .NET Intermediate language, we actually do support it.
I see. Yeah, I think that makes me quite understand how the compilation step works.
Cool. We actually work with the abstract syntax tree, with a C# abstract syntax tree, but that C# is C# abstract syntax tree is generated from the intermediate language. So we kind of take a C#. We look through the C# glasses at the intermediate language.
So like the lowered version, more or less, to speak.
Yeah, pretty much.
I see. Cool. Great. Thank you very much.
Thank you very much for the great questions. Please check out the system in more detail. And again, get in touch with me. I would be more happy to continue this conversation and answer any further questions you may have. Great questions.
That could be.
All right. Thank you very much then.
Thank
Have
you.
a nice
Goodbye.
evening. Bye-bye.
You too.